Second lecture on rings. The last time what we have defined, I think we have defined the rings with unity. What when we call the ring, ring is said to be a rings with unity if there exists an identity element with respect to the second element, right? Second operation, right? So we have last time we have defined ring with unity and also commutative rings. Commutative rings we have defined, right? So also we have seen that a subring of a CRU, that means commutative ring with unity, may not be it is called may not be CRU, right? A subring of a CRU that means commutative ring of unity may not be CRU. We have defined as seen an example of Z4, and we have defined a subring which is generated 0, 2. It is generated which is generated by 2, right? So this does not have any unity element, right? That means there is no identity element with respect to the second binary operation. So today we'll just continue with some definitions. And the first definition I am going to talk about, this is units. What is units in ring, right? So let me just give the definition of units. Unit or units, right? So let R plus be a ring with unity. For unit you must have the ring with unity. So let R, this color I see which, let R plus dot be a ring with unity 1R, right? There should be an 1R. Unity. Then an element A inside R is called a unit if there exists a B inside R and B is non-zero, which is non-zero, such that A dot B is B dot A, which is equals to 1, right? 1R. So a ring with unity is said to be, I said, a ring with unity, if you must have a ring with unity, an element A inside R is said to be unit if there exists a B inside R such that A dot B is equals B dot A is equals to 1R, right? Okay, so this is the definition of unit, right? So are we a ring with unity, and if there exists for you have an element in R. For this element you must have an element B inside R such that A dot B equals to B dot A is equals to 1R. 1R, what is the 1R? 1R is the unity element. This is called unity element. That means this is the unity element. This is a multiplicative identity with respect to the second operation, right? So what is the example? What are the examples of unit? So example, let me just give some example. Suppose you have R which is equals to Z plus dot. You know that Z plus dot is a ring. So suppose A is an unit. So what are the units of Z plus? So my question is, what are the units of z plus dot. Can you say, what can you say about the units of r plus dot? So suppose a is an unit. Let us suppose that a inside r is a unit. Sorry, r means here z. This is z, is a unit. What does it mean? If what it is equivalent to saying that there exists b inside z such that a dot b is equals 1, is equivalent to saying that a either plus minus 1. There is no other choice. Okay, so if a is an unit, so if there exists for any element a is an unit, if and only if there exists an element b such that, so for one there is a unit, so take b to be 1, then you will get 1. If a is minus 1, then you take b to be minus 1, you will get 1, right? So for these two choices you will get an unit. But if you take suppose 2, so if you have to multiply half, that will only, this is the choice of b. If you choose a to be 2 and b to be 1, you have to choose half, but half is not a member of z, so you cannot take this half. So there are units are actually basically plus minus 1. There is no other unit. So units of z are actually plus minus 1. There is no other unit. So suppose you have so the choices for a is plus minus 1. So a is a unit if there exists b inside a such that a dot b. So this b can be plus 1 minus 1, and a can be also plus 1 minus 1. There is no other choice except them. So the units of z's are, and the set of units of z units of any ring is denoted by u of z equals to 1 minus 1, right? So in any ring, the units of r is defined as this ur is, suppose this is, right? So u of r is defined as all those a inside r such that u of r is all those a inside r such that a is a unit. Okay, so this is the set which is the notation for units of the ring, right? So the clear the definition of unit, and a ring with unity, an element a inside r is said to be an unit if there exists an b such that a dot b equals to b dot a, which is 1r, right? This is the definition of units. Okay. A ring with unity is said to be a ring with unity. First of all, you need a ring with unity. After that, you can talk about the units. Otherwise, you cannot talk about the units of it, right? So the definition, I guess it is clear, right? So now I am asking you one more question. So what are the units of q plus dot? You verified that q plus dot is a ring, right? In fact, this is commutative ring, and this has a unit element, right? This has a unit element 1r. So this is actually a CRU commutative ring with unity. You can definitely talk about the units of them, right? So what are the units of them? Units of q plus dot. So suppose similarly it will go. So suppose a is an unit. A is a unit. Okay. of q plus dot, which is equivalent to saying that there exists a b inside q such that a dot b, this is equals to 1r. It is equivalent to saying that a is equals to 1 by b. These all are units. Suppose you have any a, I am giving you 1 by a, right? Then you will get 1, but a should not be 0. A is non-zero here, right? Suppose you have given you a, then I will give you 1 by a such that, sorry, here b is 1 by a, not a. Okay, here b equals to 1 by a, so f1 only b equals to 1 by a. Suppose a is a unit, then b is the choice for the b is 1 by a, right? Your choice for it is 1 by a. So but a should not be 0, right? So what are the units of q? The units of q is all those rational numbers minus 0. Every element is an unit. So suppose you have given you 4 by 5, I will give you 5 by 4. This will give us 1. This is our b. So every element is an unit. Suppose a is an unit, that this is also an unit. Similarly 5 by 4 is an unit, because 5 by 4 I will give you 4 by 5, that will give you 1, right? So every element of q is an unit except 0, right? So units of q is denoted as u of q. This is actually q minus 0, right? So every non-zero element is an unit. So suppose you have asked if you ask a question that what are the, can you give me the what are the units of, sorry, you may ask this kind of question that give me an example of a ring such that the every non-zero element is a unit. So q plus dot, this is an example of such ring, right? So now I am defining another definition of, so what is an idempotent element is a ring? Idempotent element, okay, units clear, right? And idempotent element, idempotent, idempotent, idempotent element. So let that, it is a definition, let r plus dot be a ring, right? A inside R is called an idempotent element, idempotent element if a square is equals to a, sorry, yeah, a square equals to, if a square equals to a, then we say this element is an idempotent element, right? If this property satisfies this, a square equals to a, then we say that a is an idempotent element. So, or in fact you can say that a dot a, this is equals to a with respect to the second binary operation. Okay, I will definitely talk about the second binary operation, not first. So a dot a, if so a dot a equals to 0 or a square equals to 0, right? Another definition, nilpotent element. Not I'm giving you the definition, I'm just saying r a inside the ring, r is ring, is said to be nilpotent if is said to be, sorry, just write it, is said to be nilpotent. You know the definition, I think you can guess. If there exists a k belongs to natural number such that a ki power k, which is actually 0. A की power k means a dot a dot a dot 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 a. This is k times which is equals to 0, right? This is called a nilpotent element. If such element exists, then this element will be called nilpotent element. This A is called nilpotent, right? So okay, the definition is clear. Now I am going to write a question here. This has been asked in one of the most prestigious institute exam. So I will write this question. Before that, definition should be clear. Idempotent means you should have an element a square. If it satisfies a square equals to a, then we say this element is idempotent. If there existed k inside n such that a की power k, this is k, right? A की power k is 0, then we say that this A is a nilpotent element, right? Now I am going to write a question and you definitely have to answer this question. So this question is basically a true false question. This was asked in TIFR 2019, right, for the integrated PhD and PhD examination objective paper. So the only idempotent element in the ring Z51 plus 51 dot 51 are 0 and 1. You have to say just it is true or false statement. Okay, so think about it. The only idempotent elements, that means they are saying that only 0 is satisfying 0 square equals to 0 and 1 square equals to 1. That means 0 into this implies 0 into 0 equals to 0. This implies 1 into 1 equals to 1. When do we say this is idempotent? A square equals to a, or a dot a equals to a, right? A dot equals to a. The only elements in the Z51 dot 51 dot plus 51 dot 51 is only 0 and 1. So 0 and 1 are obvious because they are all satisfying 0 square equals to 0 and 1 square equals to 1. But the question that asks is whether this statement is true or false, that only 0 and 1 are the idempotent elements. Only 0 and the 1 are the idempotent elements. Is it true? The question is saying that if there is no idempotent element, or if there is, so it will be false. So according to what will be the answer? Just think about it and try to answer whether this statement is true or false, right? So I'm giving you a solution for this, but before getting into the solution, please, I'm requesting you to please try to solve in yourself. So solution, I don't know whether it is true or false, but let me just, okay, so in Z51 we will only we will consider Z51, that means addition modulo 51 and multiplication modulo 51, right? In this ring, suppose A is an, so you have to satisfy this A square is congruent to A mod 51, right? If this equation is satisfying, so we'll say those are the elements whose are this equation satisfying this equation for every A inside Z51, right? If this equation is satisfying, then we say that it is equivalent to saying that A square equals to A under mod 15 under mod 51. So Z51 will definitely, so this is same thing, right? If this equation is satisfying, those elements who are satisfying this equation, those are the idempotence element, right? Those are the only idempotence element. So similar, clearly 0 is satisfying, 1 is also satisfying, but we are looking for whether there exist more or not. What are the elements who satisfying this equation, right, or this equality? Let me see. This is actually, what is this implies that, okay, this implies that a square minus a is congruent to 0 mod 51, because we are in Z51, so we have to consider under modulo 51, right? So what does it mean? That means that 51 divides a square minus a. It's not it. This implies, it means that a square minus 1, a square minus a is multiple of 51. That means some 51k for some k inside z, right? A square minus a is a multiple of 51. That's it. What does it mean? This implies that a minus 1 is 3 into 17 into k for some k inside z, right? So you choose from here, from this equation, you choose all those a which contains a factor of 3 as well as 17. This will definitely satisfy this equation, right? So you just you choose all those a for which a and a minus 1 will contain a factor of 3 and 7. This will given, right? So you choose all those elements a in Z51 such that a into a minus 1 contains a factor of 3 and 17. Those a will definitely satisfy this equation, right? Those a will definitely satisfy this equation. Suppose you take, suppose you take a to be 18. So what will be a minus 1? A minus 1 is 17. So a into this implies that a into a minus 1, this is equals to 18 into 17. So 17 will contain a factor of 17 and 18 will contain a factor of 3, right? So this element should satisfy this equation. So let's see what happens. So this equation should satisfy this equation, right? So let's see. 18 square is equals to 18 into 18. This actually 324. In mod 51 it is nothing but 18, right? It is nothing but 18, because whenever you will multiply it by maybe in 6, maybe 7 or 6, you will the remainder will be 18, right? So at 18 square equals to 8. So 18 is an idempotent element here. This implies that 18 belongs to 18 is idempotent. So this statement is clearly false, but can there be any other element? So you choose all the element I have so told that which contains a into a minus 1 contains a factor of 3 and 7. You choose a to be suppose 34. So a into a minus 1 will 34 into 33. So it will contain a factor of 17 and it will contain a factor of 3. So this element should definitely satisfy this equation. So 34 into 34 is equals to 34. It will be 34 square will be 34 in Z51. It will definitely. So 34 is an idempotent element, 18 is an idempotent element in Z54. So this statement is clearly false, right? So this statement is sorry. So this statement is just clearly false, because 18 square is also 18, 34 square equals to 34. So there are two more idempotent element in Z51. So this statement is clearly false. So this is false. This is false, right? So have you understood whatever I have told? Only idempotent element 0 and 1. No, there is not only 0 and 1. There are 18 also and 34 also idempotent element in Z51. Okay. So the explanation clear or not? If you don't get, then see the video again, you will definitely get. 34 into 34 square. Why 34? Because 34 into 34, whatever the number will come, it will definitely satisfy. Under you divided by 51, the remainder will be definitely 34. The remainder after dividing, the remainder will be 34. This is why that is why I have written it 34 in Z51, because 34, whatever 34 into 34, it will not be a member of Z51, but whenever you will divide it by 51, it will be a member of Z51. So it will definitely be a member of Z51, but whenever you are dividing, and the remainder will be 34, right? So that is why I have taken. Similarly for 18 also, after dividing 18, after dividing 51, you will get the remainder as 18, right? So this is one way of doing, right? So I guess, yeah. So okay, now I am defining another notion which is called zero divisor. This is an important notion, zero divisor. Zero divisor. What is the definition of it? Let R plus dot be a ring, just a ring, a non-zero element, a non-zero non-unit, a non-zero non-unit element, a non-zero non-unit. That means this element should not be zero, and non-unit means for every a, non-unit means there is no b such that a dot b equals to 1r, right? So unit, the definition of unit I have given. The last I have given just few minutes earlier I have given what is unit. Yeah, unit. If there exists a b, so there does not exist for if a is an, okay. So for zero divisor, it should be non-unit element. For unit, unit will not work here. So the ring should be the ring is as usual ring, and a non-zero, the unit should be a non-zero, the element should be non-zero, and a non-unit element is called a zero divisor if there exists a b which is non-zero inside R. There exists a b which is non-zero inside R, is non-zero inside R, such that a dot b is equal to 0, or equivalently saying that if and only if b dot a is 0. So if there exists for any a, if you get any b which is non-zero, but a dot b is giving 0, 0 is additive identity. The identity with respect to first multiple operation, first add operation, that means for addition, multiplicative identity. identity, right? So a dot b is, if a dot b is 0, then we definitely say then a is the zero divisor of the ring R, right? So for example, in Z for whatever we have taken, so 0, 1, 2, 3, right? What are the zero divisor of it? So zero divisor means 0 is a zero divisor, because 0 dot whatever element you take, 1 or 2 or 3 or 4, it will give you 0, right? So 0 is a zero divisor. 1 is a zero divisor. But whatever element you take from here, if 1 into 1 will not be 0 in Z4, 1 into 2 will not be 0 in Z4, 1 into 3 is 3, 3 will not be 0 in Z4. So 1 is not a zero divisor. To 2, if you multiply 2 here, which is 4, 4 means 0, right? In Z4, 4 is dividing by 4, it is 0, because remainder when 4 is divided by 4 is 0. So 2 is a zero divisor. Is 3 is a zero divisor? No, 3 is not a zero divisor, because 3 there is no b such that this is 0. No b inside Z4, right? This is 0 such that, so here 2 and 0 is a zero divisor. 2 and 0 are the zero divisor. Zero divisor, right? So this is the definition of zero divisor. Now I am defining another, just last definition, I guess. Integral domain. Integral domain. What is an integral domain? Let R plus dot, let integral domain, let, what is this? This is let R plus dot be a CRU, that means commutative ring with unity. For integral domain, R should be a CRU, commutative ring with unity, right? R should be commutative with respect to the second operation, right? And with unity, there exists unit, that means 1R is inside R, right? So here R plus is a let R plus be a CRU, okay? R is called an integral domain if it has no zero divisor. If it has no zero divisor, right? If it has no zero divisor, okay. I think there should not be any confusion whatever I have defined the last stage, that 0 is not a zero divisor, because 0, we are not including 0 here, so 0 is not here, right? So 0 for any element, 0 will satisfy this. If you add two non-zero element and this is give you 0, then we say that A is an zero divisor, right? Then we say 0 is a zero divisor. If you took two non-zero element, if it is still giving you 0, then we say that both elements are actually zero divisor. For B this is A, and for A this is B. They are 0, 0. So both are zero divisor. That element should be non-zero. So zero divisor is only 2 here, right? Only 2 here for Z4. So anyways, integral domain as commutative ring with unity is called an integral domain if it has no zero divisor. Okay. Nilpotent element I have defined, right? Yeah, nilpotent element I have, and nilpotent of R, the set of all nilpotent element is denoted by this set of all nilpotent elements, right, in R. And ZR is set of all zero divisors in R. And what else? Zero divisor, nilpotent, integral domain, zero divisor, nilpotent element, idempotent. Idempotent is defined as I, okay, and U unit is U. So, okay, so and I of R denotes set of all idempotents elements in R, right? And U of R set of all units elements in R, right? So this 4 notation you will only talk about. So this is nilpotent element, set of all nilpotent. This is set of all zero divisor, set of all idempotent element. This is set of all units. So for example, we have defined that R should be if R is Z4, which is actually 0, 1, 2, 3. Then what is nilpotent element in R? R means Z4. So 0 and 2, because 0 is only till nilpotent. 0 to the power 1 is 0, you can write, and 2 to the power square is 4, which is 0 in Z4, right? So this actually 2 square equals to 4 is 0 in Z4. So 2 is also an nilpotent element, right? And what is the zero divisor of R? We have just few minutes earlier I have shown that only 2, right? Because 2 into 2 is 4, which is 0 in Z4, right? So this is the actual and idempotents. Okay, are there any idempotents elements? Idempotents of R, that means Z4. R means Z4. Idempotence for 0 is an idempotent, of course. 1 is an idempotent because 1 square equals to 1.1 equals to 1. But are there any? See, 2 square equals to 4, which is 0, which is not 2. So 2 is not an idempotent element. 3 square is 9, which is actually 1, which is not 3. So 3 is not also not an idempotent. The only idempotents are this, right? So what are the units in Z4? What do you say? Unit. So A dot B, it should be 1R. So for any A, so suppose 1, for 1 there is no, for 1 there is no B, 0, you cannot take 0. 1 dot 0 will be 0. If you took 2, 1 dot 2 is 2. 2 is not 1, which is not giving a 1. Suppose you take 3 here. So 3 into 1, 3. So this is okay. Yeah, it's 0 divisor. Yeah, 1 dot 3 is 3. 3 is not 1 in Z4. So there is no. There is empty. This is empty. The unit, there is no unit in Z4. Okay. So there is no unit in Z4. Units of Z4 are empty actually, right? Have you understood whatever I have defined? So I think this is for today. Not going to too much, and later on the next lecture will define division, what is division ring and field, and will define rings or ring of integers, right? And some subrings and the criteria for checking subrings, and we'll continue in this way, right? So this much is for today. I think you got, everyone should got, and if you don't get, then you see the video again, you will definitely understood. So this today's lecture is trivial, I guess. Only definitions and some examples of rings. There is nothing special with it. And the ring theories lecture will may the total lecture will be something like, not, it will 40 lecture, it will be something like 40 lecture. I will cover the ring theory within 40 lecture, I guess. No, yeah, 40, yeah, with 35 it will be more than sufficient. I will okay, 35 or 40 lectures will be on ring theory. This is the second lecture. On the next lecture will define everything, and everything will define in a nice way. So okay, have you got? So I think I'm done with you. So this is for today. Thanks for watching. Yeah.